Hello, this is Dr. Baxley. This is part 3 of the Chapter 7 lecture video series. This is going to be about the Bohr model, which was an attempt to describe where electrons were around atoms. At the end of the last video, the discussion was about how atoms could absorb or release energy in quanta, or individual discrete packets of energy. One way this came up for physicists was that white light, like sunlight, or light from an incandescent light bulb, would pass through a prism or a diffraction grating, which is just a grating with lots of little spaces or grooves. The light gets separated into all the colors of the rainbow. And this has been known for centuries and centuries, where light would get reflected through crystals or water droplets. However, in the early 1900s, it was possible for physicists and chemists to put single elements, like hydrogen, into a tube and run an electric current through the tube for the first time in humans' history. And it would generate light when we did that. And that was really neat. And then someone had the bright idea of passing that light through a slit to make sure the light was focused, and then passing that light through a prism. Instead of seeing a continuous spectrum like was seen in the white light system, when there was just an element, a single element, shining through the prism, there were only individual wavelengths of light. It wasn't a continuous spectrum. This is called a monochromatic spectrum, and it was really strange. And it was different for different elements. At the bottom of the screen, there's a helium spectrum and a barium spectrum. And each individual element has its own fingerprint of wavelengths of light that seem to be emitted when they're excited in a lamp, such as shown in the diagram above. This really puzzled physicists for a long time. Physicists and chemists could not figure out why white light was different than the light coming out from these elemental lamps. A fellow named Niels Bohr came along in the early 1900s, and he and other physicists and chemists proposed that the light wavelengths that were emitted from different elements came from when electrons were moving from high energy to low energy as they cooled off after being electrified in those lamps. And so the different elements would give off different wavelengths of light because they had different numbers of electrons in different places. We see the effect of the different wavelengths of light, in white light at least, in rainbows. It's very beautiful. Little water droplets can act like prisms and diffract white light into all the colors of, well, the rainbow and make rainbows. It's possible to take individual element samples and put them in flame, and individual element samples will give you different colors based on, or depending on, what that element is. Another neat property of the different fingerprints of light for elements is that we can make fireworks. So fireworks consist of lots of different chemicals that are stuck into a rocket shell. The rocket shell goes up in the air and bursts, and the different colors represent different elemental compounds that are contained in the rocket shells that get excited by all the energy in the explosion and then emit the light that's characteristic for that element. Another neat feature of the fingerprints of elements is that astronomers can determine what elements are present in other planets or stars based on what wavelengths of light are either emitted or absorbed as white light hits those objects in space. So we can determine what other stars are made out of, even though we'll never ever be able to voyage to those stars because they're too far away. We can do that just by looking at the wavelengths of light that are emitted or absorbed. A couple of guys came along and tried to figure out how they could relate the wavelengths of light in the spectra of different elements to simple equations. Balmer came along first, and he wrote an equation just for the spectrum of hydrogen. But then Rydberg came along and generalized Balmer's equation to try to fit numerous elements. And the equation is pretty simple. It's this equation here on the screen. It doesn't look like a simple equation, but in reality, once we break it down a little bit, it is a simple equation. Looking at this equation, we can see that the inverse of the wavelength, those wavelengths of light that are given off by hydrogen in a lamp, they're equal to a constant divided by another constant, that happens to be Planck's constant, and that's times 1 over a whole number squared minus 1 over another whole number squared. So it's really not that complicated. We're not actually going to use this equation in class. I just wanted to show this to you to show you how it's fairly easy at first to calculate those wavelengths of light for hydrogen. The n values are just simple whole numbers, and they're related to Bohr's model that we're going to talk about right now. Niels Bohr was a Danish physicist, and he proposed that electrons traveled in orbits around atoms, like planets around the sun. He suggested that light was emitted or absorbed from atoms when the electrons moved from one orbit to the next. This would allow the energy to be quantized, because electrons could only exist in one orbit or the other orbit, and not in between. His model gave rise to the common picture that lots of people will see or draw for atoms, where the electrons move around in little circles or racetracks around a nucleus for the atom. Going back to the stair-step model for quantized energy, Bohr's orbits would be these numbers here, where there was orbit 1, orbit 2, orbit 3, and so on. And then electrons would move from one orbit to the next, either absorbing or emitting energy. Going up from one orbit to the second orbit would absorb energy, and going from a higher orbit to a lower orbit would release energy. There were some limitations of the Bohr model. So again, the Rydberg-Balmer equation was designed to calculate the wavelengths for the hydrogen atom. Unfortunately, that's all it did. The only thing the Bohr model could explain, and the only thing the Rydberg-Balmer equation could explain, were those spectra of hydrogen atoms. It couldn't do really complicated elements, like lithium or even helium. Anything with more than one electron in it just did not work for the Bohr model. Why might that be? Well, we know now that electrons don't act like small particles. They don't travel in discrete paths. But the scientists back then didn't know that. Let's go back to that double slit experiment. In the double slit experiment, here at the bottom, it's possible now to take electron beams and shine electron beams through a device with two slits in it. The electron beams end up diffracting and forming an interference pattern just like light. So in that experiment at least, electrons act like waves in that they have constructive and destructive interference. Particles wouldn't do that. However, if one takes a laser beam and shines a laser beam right behind the two slits, as the electrons are moving through the slits, the electrons can be identified as they move through the slits. In this particular experiment, the electrons stop diffracting. They only act like particles and give two bright spots. There's no longer any constructive or destructive interference. It's really strange. It's the way a particle would act, not the way a wave would act. So here's a pair of experiments that show electrons act like waves and particles in almost the same kind of experiment. It's really weird. Normal particles don't act like this. Remember that quote from Feynman at the very beginning of the first lecture video for chapter 7? That electrons and small particles don't act the way we expect them to? They don't act like big things that we can see? Well, here's one example. That electrons can be a wave and they can be a particle. Now this fellow was named Louis de Broglie. He was French if you couldn't tell by his name. And he said, "Oh, mais oui, we don't need to worry about electrons as waves or particles." Sorry for the bad French accent. De Broglie came up with an equation that said that everything has a wavelength to it. He had this equation, where mass times velocity is in the denominator, divided into Planck's constant, yet again, and that would tell you the wavelength for that particular particle. And so de Broglie said that everything had a wavelength. So everything could act like a particle. If you want to read more about how electrons can act like waves and particles, and about how weird this is, you should get the book by Richard Feynman, the physicist we talked about in the first video. And the book is called QED. It stands for Quantum Electrodynamics, which is the name of the theory that talks about electrons acting in weird ways. The first part of the book is fairly accessible. The second half of the book is way out there in terms of needing some physics. But the first half, it's worth a read if you're a physics geek. We're going to find more out about electrons acting as waves or particles in the next section of the video.